Here in ArcGIS Pro, in order to undertake an inverse distance weighted interpolation, the first thing I'm going to do is bring in my data. So I'm going to go to the Lecture 10 folder and then Overbrook and bring in both layers here, the Overbrook Aesthetics and Overbrook Hood, and I'll just drag them into my map. It shows them in their respective locations. So the neighborhood boundary here, just shown in, I guess that's pink, and then the Overbrook Aesthetics has the values and points that we want to interpolate. Let's open up the attribute table for Overbrook Aesthetics. So it has a number of different things. All of these were things that were observed at these locations to come up with an index value, which is at the very end. And it says AVG INDX, so average index. And the AVG, or average index field, contains the average index of aesthetics for each of the points. So that's the aesthetic index value. I can start by looking at things on Overbrook Aesthetics by going to the Appearance tab, Symbology, and I could do, for example, proportional symbols. And in the proportional symbols, I can choose the field AVG index. And I want to change the size from maybe 4 to 12. So I can actually don't have massive giant circles in there. Maybe 14. And that's one way I could visualize that index value. Here, for example, where I have larger circles, I have higher aesthetic values, and where I have smaller circles, there are lower values of aesthetics. And so we can start to see a little bit of a pattern in that certainly in this region we tend to have higher circles than we have over in the region right in the middle here, and higher ones over here as well. So there's kind of a middle and a mixed region in here, isn't it? It's quite mixed. So that's one way to visualize just these index values, but I want to interpolate them. So to do that and be able to have a better view as a continuous surface, I will click on the Analysis tab. In the Analysis tab, I have the Geostatistical Wizard. So I'll click on the Geostatistical Wizard. And the first thing in the Geostatistical Wizard that is asked is what method we want to use. So at the top we have geostatistical methods, 3D interpolation, interpolation with barriers, and deterministic methods. And you want to click on inverse distance weighting, and you'll see it here in blue, or maybe it won't change color. But somewhere here you'll see some place to choose inverse distance weighting depending on your version. Then the input data set, we want to make sure that's Overbrook Aesthetics, and the data field that we want to interpolate is AVG INDX, average index. And then we click Next. And because inverse distance is a very straightforward method of interpolation, what we see here is in fact our output map. Wherever we click, we can look at the Identify Result region that we see right over here on the bottom right of this Geostatistical Wizard window. So it shows X, Y, and prediction right there. So if I click here, the prediction is 3.15 as the aesthetics. If I click over here, it's 3.07, and it goes down to 2.45. You can see this bullseye happening over in this region, where we have 1, 2, maybe 3 locations with lower values and high values all around. So you can click and see what the actual prediction is anywhere. And it gives you an idea of what your output would look like at this point. You can put show or don't show the source data set. So you can turn off the points, which are the observed points, or not. You can change the point sizes, and that just makes them larger. And you can show legend. So this gives the value of aesthetics according to color that we see here as we explore. Now, the properties here, you'll see it says power too. What if we try a different power, like 1? And then we just click back over here. That's how it would look with a power of 1. That's 1 over distance. What about a power less than 1, like 0.5? Oh, I guess in this software we can't go lower than 1. So 1 would be the lowest we can go. So with 1, you see that we have less bullseyeing effects than we have with 2. Now, to the very right here is a optimize. And if I click optimize, it will find the optimal power of distance in the denominator. In this case, it's 2.14436. So it's just around inverse distance squared in a bit. Now, when it's computing these, it's only computing them based on the maximum 15 nearest neighbors. And that's fine. The reason, because inverse distance to the power of 2.14 means that locations which are outside of the closest 15 probably will have little to no influence on the value here, because the weights drop off so quickly with inverse distance squared weighting. And you can see which ones are included, because wherever you click, they turn color. So red, tan, brown, green. If I click over here, these are the ones being considered, and then these ones are not included. I can change that. I can put, let's say, this has 167, so I can say 167, so that all things will be included. And I can change my minimum to the same thing. This will have very little effect on the overall. Well, it won't let me do that. 100. Can I do 100? And 100. There we go. So generally with inverse distance weighting, you can choose the default, which is, and I'd have to recalculate that. There we go. The optimization if you change the number of points being included. But in this case, within that circle, and even outside of it, I'm saying 100 points to be included in estimating the value at an unknown location. And again, if I just go back to 15, and re-optimize, it looks kind of the same. So because the inverse distance is so quickly drops off, you don't really need to include all the neighbors in the interpolation. So now I'll just click Next. And here we have a summary that is done by something called cross-validation. And what cross-validation is if I just go back to the previous example here, is you can see that we have 167 blue dots. And if I just click on one, I'm right there. Cross-validation, so creates one of these inverse distance weighted surfaces by removing one of the individual sample locations or observations. It's removed, and then a surface is created just like this one, and then at the location where the point was removed from, we extract the interpolated value and compare it with the observed value, taking the difference. Then that point is put back in, the original observation is put back in, and then another point is removed from the data set. An interpolated surface is made with all the remaining data. At that second location, let's say right there, we extract the value at that location from the interpolated surface and subtract that from the observed value from the point we took out. And we record those differences. And that happens 167 times in order to produce a means by which we can assess how well our model, our inverse distance weighted optimized model, works in reproducing the observed values when they're not included in the data set that creates the surface. Here, what we see is the predicted values against the measured values. So measured are the observed values at the 167 points, and the predicted are the ones based on the interpolation at those same locations when they were excluded from the data set. The blue line here, or I should say the gray line that we see, is a 1-1 line. And if we had perfect interpolation models, then all of our red dots here would line up along that gray line on a 45-degree angle. And that would mean that when we remove a point, it's exactly predicted by all the other points that were left in to create the surface. And that would be true of all 167 points. So we can assess that here. So we see quite a bit of scatter. You can also click on error, which shows the measured, the observed against the error. And again, the error is the difference between the observed and the value at that same location from an interpolation of all other points. And we see kind of even scatter around there, don't we? And then we see distribution, and this is just showing the input distribution. So this is the measured values going in. This is a density form of a histogram. And we see we have a bit of a bimodal distribution going in. We can look at the predicted histogram. That bimodality is very subdued in the predictions. It just attenuates the this rising limb. Measured and predicted together, or just the error. And we see a little bit of bimodality in that error. But generally you want to have the errors to be normally distributed, to have more of a bell shape, if possible. But we're limited with inverse distance squared. Finally, we have a root mean squared error right here. And this is in the units of the measured values or observed values. So this is 0.41 aesthetic index units. And you want that to be as close to 0 as possible, depending on what type of data you're looking at. Finally, I'll click Finish. And it gives me a method report right here of the data set that was used. The power, the only parameter in inverse distance weighting is the power, and that was this one here, which was optimized. And then the neighborhood search, how many points were used to create each interpolated estimate. 15. So everyone had 15 being used. And I click OK. Then I just have to turn off my Overbrook hood and I'll see the prediction behind there. So here we can see then we have our layer, which is an inverse distance weighted interpolation. Now it may not look pretty, and if I put the Overbrook hood on there, you can see that, well, I'll move it behind as well. It's, remove these old things too. It doesn't conform with the neighborhood boundaries. And there's a reason for that, in that anywhere outside of the points, even up in the corner here, is extrapolation. All the way down here as well, just as my mouse is in kind of this line here. That's also extrapolation. And so extrapolation is not something that you want to do very often with interpolation, unless you know there's a good reason to do it. But if, for whatever reason, we want to have a complete representation of a continuous surface within the Overbrook polygon, then we have to do this through the toolbox. But before we do that, we have to set some environment settings critical to the geostatistical analyst tools and also critical to raster analysis. So I go to my environments, and my extent, I'll have the same extent as Overbrook hood. So I'll choose Overbrook hood. Mask, Overbrook hood. Cell size projection method, preserve resolution. Cell size, we'll just leave it maximum of inputs for now. We don't have any rasters to snap to. So the main thing here is the extent and the mask. The mask will be the outline of the Overbrook hood, neighborhood, and the extent will be the extent of the Overbrook neighborhood. So then we have to go over to the Toolbox Geoprocessing tab, to Geostatistical Analyst Tools, Interpolation, and this is where we can find all the same methods. We want IDW, and we want to interpolate Overbrook aesthetics. The Z value field, average index. The output geostatistical layer, well, whatever we want to call that. Let's call that the AESTHETICS aesthetics. And the output raster layer, we'll call it aesthetics RAS. Cell size, let's choose 2, so it's nice and fine scaled. And then we have our power. We'll put 2.14, which we found through the optimization, and min and max neighbors 15, both. And then we click Run. And we wait for that to complete. Up comes the completion, and I'm just going to turn off my points to start with, and I'll turn off the aesthetics RAS, and then we see our geostatistical layer, which honors the extent but not the mask. So I'll turn that off, and I'll just turn on now back to the aesthetics RAS, and I'll turn off the old inverse distance. And now we have an inverse distance layer, which is within the boundary of Overbrook. But remember that the things we see here, just take a second for that to open. If we look at this, all this region down here is extrapolation. We have no support for that area. Support meaning observed data. Likewise up here, no support. Even in here is difficult because there's little support. No support. So the only region that we can really interpolate within is the region within which we have support, which is where we have our data. And of course we see the bullseye effects, as I talked about earlier.